book at the moment, and we will be talking about Abelian quantum gauge theory via differential formula.
Okay, thank you for the nice introduction, and thanks to the organizers for inviting me here. I will speak also about Abelian gauge theory like in Cosender's talk, but I will focus more on geometric problems instead of physical interpretation. So I will tell you about a quite, in my opinion, very efficient way to describe Abelian quantum gauge theories via a geometric tool called differential cohomology. And this is work in progress with Becker from Potsdam and Richard Szabo from Edinburgh. Okay, so my motivation comes essentially from two questions. And the main question, which is now in the round since quite some time, is why does gauge theory fit into the axioms of locally covariant quantum field theory, which were written down by Brunetti, Friedenhagen, some 10 years ago maybe. So this goes back to an observation due to Pontryagin and Benjamin for a kind of gauge theory. It's not really a gauge theory, but related to Maxwell's theory, where you describe the gauge field via the field strengths. And they observed that in such a theory, if you formulate Maxwell field strengths, you have maps from space-time to bigger space-times, such that the maps between the algebras are not injective, which is somehow weird, because you go to bigger space-time and you lose observables. A kind of weird observation. There came a physical explanation in a paper by Claudio, Thomas, and Co-Sanders, and Co-explained it to you in more detail on Monday. And it is, their explanation is that electric charges mess up the locality axiom. Locality axiom simply means that these guys should be injected. So violating locality axiom means I have maps which are non-injective. So Co explained this to you in a little bit more detail in his talk. He called this also Gauss law, but it's electric charges. So a more mathematical explanation appeared in a paper I've written with Marco, Claudio, and Thomas in a theory focusing on connections on bundles. And our observation was that the quantum field theory functor has a subfunctor which is purely topological in a sense which I will make later more precise, and is related to some compact supported around homology group. And this purely topological subfunctor, which you might call a topological quantum field theory, is the reason for this behavior. And I will later give you the more detailed explanation and also a little bit more advanced explanation than we gave here. So here we were talking about electric charges, and the question is, okay, electric charges, we also could have magnetic charges, which are monopoles, Dirac monopoles, and do these magnetic charges behave similar to the electric charges? Of course, when you want to answer this question, you have to include them in some reasonable way, which is not done when we formulate in terms of gauge potentials of theory. What you have to do is, in order to understand these magnetic charges, you have to look in a physics book, and people will tell you, instead of integrating in a path integral over connections, you also have to make a sum over all bundles in some way. And if you read this first, you ask yourself, how can this be done? How can this ever happen? And differential cohomology gives us, first of all, an explanation what this means. And second, a very straightforward overview, a very precise overview over these features here. And this is what I want to explain to you. And as a byproduct, this doesn't work only for Maxwell, but also for all sorts of higher generalizations of Maxwell, like connections of gerbes, which are not relevant in physics, but in string theory. But okay, if you want, you can also look at the gerbes. So in my talk, I will start with telling you what is differential cohomology. This I have to do because up to some months ago, I was also not familiar with these techniques. Then when I explain to you what is differential cohomology, then I will study generalizations of Maxwell equations in this language and their solutions to these equations. Then going from configurations and solutions to observables, I made some observations concerning a good class of observables, which I call the smooth Pontryagin dual of these cohomology groups. And on these smooth Pontryagin duals, you get everything you need for a classical field theory, namely a pre-symplectic structure, and then by usual canonical quantization, slightly generalized you can get to a quantum field theory and study its properties. And then I will conclude it. Okay, what is differential cohomology? I start from Maxwell theory, I end up at differential cohomology. So in Maxwell theory, the first observation is what are the degrees of freedom of Maxwell theory? So Coe asked himself a similar question in his talk. He said it's connections. But I'm going one step further and I say, okay, connections on which bundle? Should I fix a bundle from the beginning, or should I say these bundles are parts of the dynamical degrees of freedom? And this is the point of view I want to do, because I want dynamical magnetic charges, so I have to take care of all bundles at the same time. So the degrees of freedom are bundle connection pairs, and a special kind of bundle, emission line bundle and emission connections, because we want to formulate U1 gauge series. So I can pack all of these pairs in a big set, the configuration space, and the configuration space has a quite easy algebraic structure, namely it's a group. I can add bundle connection pairs by simply taking tensor products of emission line bundles and the sum of connections, so the connection which is induced on these tensor products. So the configuration space is an abelian group, but far away from being a vector space.
But this would be only a semigroup.
No, it's group. You can invert these things, because you can take the bundle with the opposite. So the unit element is the trivial bundle with the trivial connection. And if I take a bundle with some opposite Chern class, so by inverting the transition functions in the regions and taking also minus the local connections, then I get to inverse. So this you can easily check in, say, local patches. You describe the bundle by transition functions, then you know how to invert, and the connection by local one forms, then you know also how to put a minus in the game. So this is a group, really a group. This is a specialty of U1. If you take generic vector bundles, then it's a semi-group, and this is what people in K theory do. But here in U1 case, it's special, it's a group. Abelian even. Okay. So on this big set of configurations, I have the notion of gauge equivalence, yes, because two such bundle connection pairs are equivalent when I have a bundle isomorphism between these two, preserving the connection. So with this notion of gauge equivalence, I can form the gauge orbit space, which I denote here by a weird symbol, which becomes clear later while I use this weird symbol. And this is also an abelian group. So the configurations modulo gauge of Maxwell theory is an abelian group. So configuration space is an abelian group. But this group has somehow nice properties, because what can I do when I have a bundle connection pairs? I can calculate the curvature of the connection. So I have a map from this configuration space to the forms, two forms. This set simply means that they have integral periods, so this is Dirac charge quantization condition. So I get only forms which have integral periods, comes from the fact that this is the curvature of the connection. Okay? So, and this is also AP, so it's a surjective map here. I can get for any form of this kind, I can find a bundle connection pair which produces a solution. This is a standard result in bundle theory. Okay? Then I have one more nice map, namely, to each bundle connection pair, I can associate some topological information, namely the first Chern class of my bundle. This is also invariant under this gauge equivalence, so I have two nice maps. These two nice maps have kernels. Yeah? For example, the curvature map has a kernel, and this is what people call the flat connections. And this is maybe what is not so obvious from the beginning, why flat connections are the certain value cohomology group. But you might think of flat connections as determined by their Wilson loops. And the Wilson loops of flat connections, when you put in a boundary, instead of the one cycle, one boundary, it's trivial because they don't have curvature. So this is really the correct thing, classifying flat connections on a manifold. Or flat bundle connection pairs, to be more precise. Then also the characteristic class has a kernel. Namely, I have a trivial bundle which has no characteristic class. And gauge equivalence classes of connections on the trivial bundle, which is exactly this quotient, which you maybe have seen in Coe-Sanders' talk. This is the kernel of the characteristic class. Okay? So far so good. This is now a little bit more complicated to read this diagram, but everything which I said now you can pack in a nice diagram. And this nice diagram comes with exact rows and columns, okay, by what I told you before. And here is the configuration space, the gauge orbit space I'm interested in, and here are the maps I introduced. The curvature map, characteristic class map, the kernel of the characteristic class map, the kernel of the curvature map. And this outside stuff is now not important at the moment. This is obvious, this line here is obvious. This is some coefficients, coming from some coefficient sequence in cohomology, and this is universal coefficient theorem, just in case you want to know. But the important thing is this cross here, yeah? The interesting guy sits in the middle, and the cross are exact sequences. Okay? So this comes from this reasoning of looking at bundle connection pairs and looking at their gauge equivalence classes. I end up with such a diagram. And you see here there is some index 2 in the game. Here some 2 minus 1, which is 1. So this is of a certain degree, and the question is, can you make sense out of such things also in higher degrees, for example? When I go higher degrees, I go, for example, to higher form curvatures. And this is indeed the case. I draw the same diagram, but I just replace 2 by star, so meaning graded, and 1 by star minus 1, meaning graded shifted by minus 1. So I draw the same diagram, and I call this diagram a differential cohomology theory, or let me be more precise. A differential cohomology theory is a functor, Pontryagin, from manifolds to graded abelian groups, together with a bunch of natural transformations, which you should think of curvature, characteristic class, inclusion of the topologically trivial inclusion, and flat connection inclusion. Yeah? These 4 transformations we had before, and this diagram should convolve and has exact rows and columns. And indeed, this diagram specifies everything you need, because there is a theorem which is quite recent. This is 2008 by Simons and Sullivan, and this was done in a slightly more efficient way in 2013, I think, by Becker and Becker. And differential cohomology theories exist. Okay, this is known since the 70s. Giga-Simon theory is an example, but they are unique up to a unique natural isomorphism. So if I give you that diagram, this guy in the middle, which is the gauge orbit space of a gauge theory, is uniquely determined just by this diagram. And this is why this language is very efficient. Namely, I don't care about this guy in the middle. I want to formulate a theory based on this guy in the middle, and I can describe it just by looking at its surrounding, which are spaces which are easy, like torsion subgroups and cohomology groups and forms. These are standard stuff. And with this standard stuff surrounding, I describe this guy in the middle uniquely. So this is, in my opinion, the nice thing about differential cohomology. So let me give you some examples. When going to different degrees, you get different theories, which might or might not be of physical interest to you. So in degree k equal 1, this might be a model which is physically interesting, namely a sigma model with a circle as a target space. Because there you can easily check that this differential cohomology group, say one model for this group, are the circle value functions. The curvature of a circle value function is the logarithmic derivative of this function up to some prefactor, so it's a one-form field strength, like this one here. And the characteristic class of the circle value functions are the winding numbers around the circle, which are described by this cohomology group. Now in degree k equal 2, and this was my motivating example, this is Maxwell theory, so bundle connection pairs, you one bundle connection pairs. Modulo gauge equivalence is a model for this group. And my curvature gives me a 2-form field strength, and the characteristic class map gives me a Chern class. Now I go higher to k equals 3, and I end up at higher Maxwell theory. One model for this is gerbes with connections modulo equivalence. So gerbes, what it is not important right now. Think of it as a higher version of a bundle. But higher versions of bundles with connections modulo equivalence, you get 3-form field strengths, and you get charges living in a higher cohomology group. And these people call that X-mutuality. And if you go even higher, then you get higher to some more powers Maxwell's theory. So you can go arbitrarily higher. Of course, at some point it gets boring when the degree is higher than the dimension of the manifold. This stuff gets trivial. Okay? So I can go up to the dimension. which is in 4 dimensions, I cannot go so much up, but in, say, 11 dimensions, you can go much up, and this is why these higher things people are using in supergravity, for example. Okay? So, this was the introduction to differential cohomology. Now let's look at a little bit field theory applications of this differential cohomology. So, in order to make some field theory, I go also to such a category of manifolds, to spacetimes, globally hyperbolic spacetimes, like Chris introduced in his talk, but I make here explicit dimensions. So these are n-dimensional spacetimes, globally hyperbolic, with orientation, type orientation, and the standard things you need, and the good maps between them as morphisms. Okay? In this, working on this category, I have a further nice natural transformation in the co-differential. And using the combination of the co-differential with the curvature, I get something which, for obvious reasons, people call them, or I have called them Maxwell map. Yeah? This is like Maxwell equation or Maxwell operator, maybe also higher degrees if you want. So this natural transformation is then my equation of motion, and I want to understand the solutions of this equation of motion. And the solutions are the kernels of this map, and since this is an abelian group, this is a group morphism. The kernels are also abelian groups. This is why I call them solution subgroups. So the solution spaces are abelian groups like the configuration spaces. This also is characterized by a diagram, namely these solution spaces are a subfunctor of the configuration spaces, and they fit in a diagram with nice rows and columns. Here, this sol K is the solution space Ko was talking about, the solutions on the topologically trivial bundle. They inject into the full solutions, but I have, of course, also solutions for any other bundle attempt. So this is the surjectivity of that map. And so we can also characterize solutions in a nice way by such a diagram and sequences. And I didn't look at the Cauchy problem, but at some weaker statement than the Cauchy problem, namely, when I have a Cauchy morphism, so a morphism which maps, which has in its image the image Cauchy surface of the big space-time line, then the map between solution spaces is an isomorphism, which simply means that if I have local solutions around the Cauchy surface, they uniquely extend. So the dynamics you get from this generalized Maxwell map is indeed good. It's uniquely, you can extend uniquely local solutions to global ones. This you could call a classical time slice axiom, which is slightly weaker than the Cauchy problem, because the Cauchy problem would require me to make it sharper and sharper, the localization around the Cauchy surface. Okay, so this was now the discussion of configurations and solutions, but like, for example, what you heard in Kasha's talk, it's also important to look at functionals, because functionals are observables. So functionals should then be maps from this group to the complex numbers. Since my configuration space is an abelian group, there is a preferred set of functionals, namely group characters. So group homomorphisms from my configuration space to the circle group. This is a preferred set of functionals which I have since my configuration space is an abelian group. This I denote by star. These character groups I denote by star. Of course, the character groups are not a star algebra, but just an abelian group. But it's clear that when I take, when I span, or when I allow for sums of these group characters, that I get an algebra, that I can generate an algebra out of it by C-linear completion. So I will look at these character groups, and I will make the algebra later when I understood the character groups. But the character groups are somehow sick. I didn't tell you anything about topology or a smooth structure on this here. So I take arbitrary group characters, which are ultra much. And I didn't assume any continuity, regularity, or something else. So what should we do? And what my suggestion was, what one should do is that one makes the following observation. If I, for example, now look at the P-forms, which I forget everything but the abelian group structure, then the character group of the P-forms has a nice subgroup, namely the compactly supported smooth P-forms. In the following way, to any compactly supported smooth P-form, I can associate a group character, by simply smearing and exponentiating by some complex imaginary exponential. Yeah. So here this is the usual inner product with the Hodge star. So in this way I get the subgroup of the character group, which is distinguished in the sense that it is the character groups which, when I would define functional derivatives, give me regular functional derivatives. So this is what I would call the regular characters. But then some people were faster than me, Harvey, Laws, and Zweck. They did this already some years ago because they studied the duality of differential characters, and they called these subgroups smooth Pontryagin duals, which is not really fitting up the way I would call them. But so I will stick to this notation not to make everything more confusing than it is. So I would call, when I talk about smooth Pontryagin duals, I mean this kind of regular Pontryagin duals, where the functionals are of this exponential type and regular. Okay, so this was now for the example of the P-forms, but now if you remember this diagram, which is far away back, I had more complicated spaces. I had quotients of form spaces, and I had forms with some restriction, like integral periods. And so I have to understand also for these form spaces, there are smooth Pontryagin duals. So the aim of this, what I want to do now, is the following. You remember this big diagram describing the configuration space? I want to make a dual diagram of it. And dual diagram is very easy with the home functor, because the circle group is a divisible group, so it's an exact functor, it preserves exact sequences, and we get, for applying the full character groups, we get a nice diagram. But due to my argument before, the full character groups are way too weird, they are distributions and more weird. So I want to dualize and then restrict to the smooth Pontryagin duals, and so I have to tell you what are the restrictions to smooth Pontryagin duals. And what is clear is that every group which is sort of discrete or like these Z-value cohomology groups, these are discrete groups. There I don't have to do any tricks. So when I have the ordinary cohomology groups, then I take a smooth Pontryagin duals, the full character groups, because I have no reason to restrict to regularity, because these are finite dimensional things. Everything involving differential forms, I follow the strategy above and go to these smooth duals. Okay? So this is now a weird piece of my slides, which is maybe too complicated, but which I try to explain the basic idea. Namely, what would be a good character group of this quotient space of k-1 forms modulo integral period k-1 forms? Of course, when I wouldn't do the quotient, I would say, okay, the compactly supported k-1 forms give me good characters on this. But now, not any compactly supported k-1 form gives me a good character on the quotient, because it has to be compatible with taking the quotient. So I am only taking those compactly supported k-1 forms which vanish on this group I talked about. So this is a reasonable way to do. When I want to do a quotient of a space, I take a restriction. Also, I take only those functions which vanish on this thing I want to quotient out. And this is here exactly what I'm proposing, to use these vanishing groups as smooth Pontryagin duals of that group here. Now, this is some easy check. When you have exact forms, this kind of thinking of smooth duals produces a co-exact compactly supported forms. When I have forms which have integral periods, then of course I take the full, I can of course act with any compactly supported form on them. But some of these characters are trivial, namely those which are annihilating this group. And so it's the same vanishing subgroup as here. I have to divide out to correctly count the dual group of that one. Okay? And now this is the trick which is similar to what the Harvey laws did. I now understand for the topologically trivial theory a good notion of duality. And I use the maps I have in my big diagram to say what I mean by the smooth dual of the differential cohomology. So I take the dual of this topologically trivial inclusion and I pull back and I say this is my smooth dual. This is, of course, you might think this is weird what I'm doing, but it's not so weird, because Because all these groups I'm defining here are covariant functors, so it's somehow not too bad what I define. And even more, they separate points on the Abelian groups they act on. So I'm not restricting myself too much in the function. I can still separate two different configurations, which is quite good. Okay, so good. And now for these smooth Pontryagin duals, you can cook up again nice sequences and the diagram. So you dualize via the home functor, this diagram we had before, and then restrict at these places where character groups of forms appear to the smooth duals. And here also you see that this still is a commuting diagram with exact sequences. So also the observables or the observables of a special type are described nicely by the diagram. And I never was saying what I mean by this, I just was looking at the diagram. So you still don't know what is in there, you just know that it's in the diagram and this is enough. Okay? And this diagram will tell us data a lot about the classical and quantum field series. So just to give you a kind of preview, this I interpret as a special kind of observables of my gauge theory. Then I have sitting in this special kind of observables even more special observables, namely the ones measuring curvature. The curvature observables I can map into the full observables, so this is good. And even more, I have observables which measure the germ class or the characteristic class, and I can also map them in the full observables. So I'm seeing here already some kind of subtheory structure, and this is the one which later will tell me why the axioms of locally covariant quantization are not perfect, okay? But before that, I have to go on a little bit, and because just having spaces or groups of observables is not enough, I also need some forsortens or some pre-symplectic structure on these. So a nice way to get a pre-symplectic structure is to use Payet's method. And for using Payet's method, we need some Lagrangian. The Lagrangian, I'm using the obvious generalization of Maxwell Lagrangian and taking the curvatures, wedge them and put a Hodge star in the middle. This is normal Maxwell Lagrangian when I'm in degree 2. And Payet's construction also works for functionals, but this we can easily achieve because any group character you can consider as a functional simply by embedding the circle in the complex numbers. So you can understand any group character as a functional, as a special kind of functional, taking just values on the circle. And I can apply Payet's construction. But there's still one thing which is missing, namely I have to say how to do the functional derivative. What is the manifold structure on these weird differential cohomology groups? Fortunately, you can guess a functional derivative, which also seems to be correct when you come from an infinite dimensional manifold direction, which is unfortunately still work in progress. We understand this in full detail. But there is a way how to define a functional derivative, and for this I maybe draw a nice picture, which I should have drawn 15 minutes ago. Sorry for that. This configuration space. From this diagram you see how it looks like, namely it has many disconnected components. These disconnected components are always like infinite dimensional planes and some torus vibrations over them. So you have here, this is labeled by H2MZ, so by HKMZ, so the characteristic class is labeled and the disconnected components. These are the different topological sectors. Here, this is the field strength information, and here in this tori, they are the Aharonov-Bohm phases. So the configuration space has this form. And now, of course, it's obvious from looking at this picture what is a continuous curve in this thing. I don't have to define topology. I just look at this picture and think about what could be a continuous curve. And I simply take in this torus vibration sort of the easiest negative. If this would be a plane, then I would take linear curves. But since this is a torus, I take linear curves when I unwrap the torus, so to say. So I take these special linear curves and I can make the derivative along them. And this is done here. So it turns out that the correct tangent vectors are gauge potentials modulo small gauge invariants. Yeah. So these are the correct tangent vectors, and this comes also out from looking at the geometry of these things from a more rigorous point of view. So along these tangent vectors I can define my functional derivative, and there, as expected, an exponential function reproduces itself, and I get down the exponent. Pull it back a little bit. Okay. So this is quite good. I can make the functional derivative, and then I can calculate the Poisson bracket between such observables, and I see that this Poisson bracket comes from a pre-symplectic structure, which is that one with a cross propagator inside. So this follows from Peierl's construction. This I don't have to guess. This you can calculate. Okay. Here it's nice to see that the pre-symplectic structure is indeed a pullback of a pre-symplectic structure on the topologically trivial theory, because here this dual of the topological trivialization enters. So this will be important in a second. So I get a pre-symplectic structure, so I can equip my smooth Pontryagin tools with this structure, and I get pre-symplectic abelian groups, and pre-symplectic abelian groups is one possible model for classical theories. Okay? So, and this is what I said. I use this pre-symplectic structure, and notice that I obtained it from pullback of a pre-symplectic structure on the topologically trivial theory, and I now can construct a full list of classical theories, namely the full classical theory describing the full set of observables of the gauge theory. Then I have the topologically trivial classical theory, which is similar to the one Co has shown you. And then I have the classical curvature theory. I obtain all these pre-symplectic structures by pulling back along the arrows in this big diagram we had before. And I have a classical purely topological theory, which is a cohomology functor, or the Pontryagin tool of a cohomology functor, which is a homology functor, and has a trivial pre-symplectic structure. So I have a bunch of theories, and due to this big diagram I had at the beginning, this bunch of theories fits in a diagram, which is now not anymore so symmetric, but as I explained later on. It still fits in a nice kind of diagram which tells you a lot about the structure. This is the classical theory. It has a subtheory measuring curvatures. The subtheory measuring curvatures is injectively embedded in the full theory. I have another subtheory measuring cohomology classes. This is what physicists call magnetic. And this is injectively embedded in my full theory. So I have two sorts of subtheories. One which you might guess that just observing curvature is for sure a subtheory. But this one is just observing topology, which is a topological subtheory. And my big theory projects down to the theory Sanders was describing. So I can forget about this topological aspects, and I can project it down and get the thing was describing. Okay? Good. So this is I forgot to say, this is for off-shell. I didn't now quotient out the equation of motion, but this I will now do quickly. So the rule of thumb is on-shell is equal to off-shell modulo vanishing subgroups. So I quotient out everything vanishing on solutions. This is also similar to Kasha did. And if I do that, and if I denote everything by the same symbols, then even more subtheory structure exists. Namely, here in this curvature theory, there is a further subtheory, also purely topological, because it's again the cohomology theory, or the Pontryagin rule of cohomology theory. And this is what people call electric. So you have an electric subtheory and a magnetic subtheory sitting in your full theory. Okay? So when I have two things which look weird, then I sum them up to have just one thing which looks weird. So I take the sum of these topological subtheories. And I know that it's really topological because this guy just depends on the homotopy type of spacetime. So it doesn't know anything about metric and so on. It's just depending on the homotopy type. So I can, for example, contract away the time and I don't get anything differently. So this is really a topological theory. So how about quantization? This was now the classical one, and quantization also for these more complicated things is not too complicated because pre-symplectic abelian groups can be also treated with the usual wild quantization. If you slightly extend some older results by Manusov, which we have done with Marco, Claudio, and Thomas, then you get also a CCR functor for pre-symplectic abelian groups. So this abelian group structure doesn't matter there. The pre-symplectic simply means that the Wien algebras are not any more simple, but this is clear because I have some kernels, centers. Okay, then one warning. CCR is far away from being an exact functor, and it's even weird to think about what is an exact sequence in the category of unital C-star algebras. So this CCR quantization does preserve the sequences I was showing you, but fortunately it preserves injective groups. So everything which was injective between the pre-symplectic abelian groups, it stays injective between the C-star algebras. So this is good. So it preserves the subtheory structure we have found. And from this now, I can think about how it works with these properties you want the quantum field theory filter you obtain from this CCR quantization to satisfy. And of course, causality is trivial to see because we have the causal propagator in the game. There always causality holds true. Time slice axiom follows from the classical version of time slice axiom I was showing you at the beginning. And this locality axiom, which means that the morphisms which I get from this functor are injective, is violated in general unless you're living in 2 dimensions and looking at the circle value field. So in everything interesting, the locality axiom is violated. And so you might ask, why is this locality axiom violated? And here is the answer. The violation of the locality axiom is only connected to the topological subtheory. So if I have a morphism between manifolds, then the induced C-star algebra morphism is injective if and only if the morphism between these charge groups is injective. So it is only due to the purely topological subtheory, it is the only source of violations of the locality axiom. So it just comes from this, from nothing else. Or even more easier words, electric and magnetic charges are the only thing that screw up locality in a abelian gauge series. Okay, this is now my main statement here, and it is really due to these topological subtheories which I think BFE didn't consider in 2003. But maybe you can tell me later during the coffee. Okay, so let me conclude. So I hope that I convinced you that differential cohomology is a very effective technique to construct abelian gauge theories in any degree. So bundles is not special, you can do any higher gerbes, and it works the same because I never have to look at the configuration space itself because I'm indirectly describing it by its surrounding cloud of other spaces which are easy. So from the fundamental diagram and exact sequences defining a differential cohomology theory up to isomorphism, you see already a lot of properties of the quantum field theory. Namely, you see that the quantum field theory has subfunctors, some of them being fancy, being just dependent on topology. So the most interesting subfunctor is the sum of these 2 topological subfunctors, which doesn't see any metric, doesn't see any causal structure, it just sees the topology of space-time and even just parts of the topology because it just sees the homotopy type of space-time. So I would say it's fair to call the quantization of this subfunctor, so the subfunctor in the quantum case, the topological quantum field theory. Of course, I would say Attia doesn't agree on this, but I think from the point of view of algebraic quantum field theories, this is a topological subtheory. This is a topological quantum field theory because it just measures purely topological information, nothing else. And this purely topological quantum field theory is sitting inside gauge theory, and this is what screws up the situation. So, abelian quantum gauge theories have topological subquantum field theories, and the locality axiom is violated because of them and not because of something else. Okay, so open problems and work in progress. So as I said before, The diagram at the end describing the subtheory structure of my theory was slightly asymmetric. There was some part missing, and what was missing was the group of flat characters, the group of flat connections. And this group of flat connections has a different role, I think. Namely, I think that this is a local symmetry group, which is not a gauge group. And this is something I tried to discuss with Chris already, but we are not yet sure how to do that. But I think this was in your outlook the same. Local groups, which have some different features. Related to this, I think, is the representations with these theta angles, which some people write down in the path integral, and swapping these thetas and the stuff which comes from flat connections is what I think is Abelian S-duality, but this we don't know at the moment how to prove this in detail. Okay, and last but not least, everything I said you can replace ordinary cohomology by any generalized cohomology theory, for example K-theory. And you can also look at gauge theories where the charges live in K-theory, for example, which people call the Ramon fields. Okay, thank you.
Thanks, Alexander, for the nice informative talk and questions.
If I got it correctly, your space of observables have its own configurations, but is it true that it's also optimal in the sense that...
It is automatically optimal because it's a character group. The separating in the other slot is automatic because I'm having, so to say, observables in a representation, and this takes care of it. So it's automatic.
Questions?
So I think the appropriate generalization of these axioms of local equivalent field theory would be to restrict oneself to topological trivial spacetimes, because it's well known that for gauge theories you have different possibilities to associate algebras to regions. It's not unique. Actually, this holds already for non-connected spacetimes.
Yes.
You have gauge symmetries. Even then there are several possibilities to associate algebras to this. So my question is the following. When you restrict the functor of the field theory to the topological trivial regions, then you can ask the question, what are the possible extensions to spacetimes which have non-trivial topological structure? Could you recover this structure generally?
This is what I don't know, but this is something I was talking about with Benny Lang and Chris. Namely, they are doing this universal algebra construction, which gets out something else. Like the universal algebra construction, for example, forgets about Dirac charge quantization. So the cohomology classes of the curvature are then in a real space, not in a lattice. So the universal construction forgets about some important gauge theoretic aspects. What I think what has to be done is one has to remind the universal construction about the relevant charge groups in the gauge. Yeah? And the charge groups are...
Can you discover the charge group from the original structure? So here this seems to be that it's...
so here the charge groups are
definition of the theory. Yeah, you start from a certain classical theory which has certain properties, and that's the basis of your analysis. But it would be nice if you could derive it like in the spirit of the theory of superselection, yes, where you start from the observables and then recover the gauge group.
Yeah, this is what we don't know at the moment, because this is what we don't know at the moment. Because it's mysterious to know how for the main question one has addressed is the Dirac charge quantization condition. So this is something which I would like to see coming out by patching local algebras. And the universal algebra doesn't do that. And it also forgets about flat connections. So there is certain things which the universal algebra does wrong or different. Namely, it takes too many magnetic charges into account, not only the quantized ones, but continuous ones, and it forgets about flat connections. And as well as the magnetic charges and the flat connections are both described by cohomology groups, which maybe one has to modify this construction somehow to enforce that. I don't know, you don't want to enforce these things, you want to get it out, but I don't know how.
Ego?
Right. So, in my understanding, the reason that some mathematicians love these differential cohomology theories because they, in some way, generalize cohomology groups, which are invariants of manifolds, and these are finer invariants. But from the point of view of physics, forms, which are the fields that you're talking about, are very special kind of fields. So, when one starts talking about linear fields that are not forms or even nonlinear field theories, I imagine a lot of the structure that you described, like the Abelian group structure and so on, disappears.
Yeah.
So, I mean, if you are dealing with some kind of possibly nonlinear field theory, but which has possible non-trivial bundle structures and gauge, like what is the thing that you need to keep to describe the configuration space in that case?
I think what is the I don't like this approach, but this is what people tell me what you should do in the non-Abelian setting, and this is in some check setting. Yeah. So because in a local patching version you can go non-Abelian and describe sorts of non-Abelian bundles in its higher versions in a check language. What I don't like about this is the cover I have to take at the beginning, but there should be a way to remove this at the end. So one should go to a this easy diagram with Abelian groups is not anymore there in a non-Abelian theory, but there's with the spirit similar things there, which you make, because this differential cohomology is equivalent to the line cohomology, and the line cohomology you can go better in non-Abelian.
But so you were calling some of the theories that are described by this construction, well, you described them in terms of gerbes. And I'm not sure if gerbe is the right mathematical structure that will remain in generality.
It's not.
So what is the mathematical structure that you'll need?
For describing what?
Well, say nonlinear field theories.
Non-Abelian gauge series.
Gravity, for example. Supergravity, there are lots of examples.
These models are just describing parts of such series.
Okay, right, thanks.
Okay, so perhaps the last short question, if you have. Otherwise, we have to do it. Okay, so since we are running out of time, I would like to thank Alexander again.